So we'll start by definitions. A simple curve is a curve that does not cross itself. Starting and stopping may be the same. It doesn't have to be, it can be. A closed curve is a curve that starts and stops at the same point. A polygon is a simple closed curve with sides that are line segments. A convex curve is a simple closed curve with no indentations. The segments connecting any 2 points in the interior of the curve is wholly contained in the interior of the curve. A convex curve is a simple curve with no indentations. The segment connecting any 2 points in the interior of the curve is wholly contained in the interior of the curve. If I pick any 2 points on the curve, the line segment connecting them has to be inside the curve, not part of it can be outside. A concave is a simple closed curve that is not convex. It has an indentation. Let's look at some curves and we'll determine if they're simple, closed, polygon, convex, or concave curves. In the first case, it starts and ends at a different point. It doesn't overlap itself, so it's a simple curve. It is not closed, so it cannot be a polygon, convex, or concave curve. In the second curve, it starts and stops at a different point, so it's a simple curve with no overlaps. And since it's not closed, it cannot be a polygon, convex, or concave curve. For the third curve, it starts and stops at the same point, so it is a closed curve. Since there's no overlaps, it is a simple curve as well. It cannot be considered a polygon because the curve doesn't consist of line segments. Now, is it convex or concave? Well, if I look at a point here and a point here, that segment is outside of the curve. So it cannot be a convex curve. It must be concave because there's actually an indentation. For the fourth curve, it is a simple curve. There's no overlaps. It is also closed because it starts and stops at the same point. It is not a polygon because it does not consist of line segments. Now, is it convex or concave? If I look at any 2 points on the curve, that segment is completely contained in the curve, so it must be convex. This curve overlaps itself, so it cannot be a simple curve. It is a closed curve. It starts and stops at the same point, so it is a closed curve. It cannot be a polygon even though it consists of line segments because the definition of a polygon requires it must be a simple closed curve first. And it cannot be convex or concave because it must be a simple closed curve first. The last two graphs are both simple curves and they're closed curves. They start and stop at the same point. They're also both polygons because they consist of line segments and we don't have any overlaps. For the first curve, there is no indentations, and if I draw a segment in the interior of the curve, there's no way that line segment will ever be outside of the curve, so this must be convex. For the last curve, if I draw a point at the base of the curve, this segment is outside of the curve, so it is concave, and it also has an indentation. Every simple closed curve separates the plane into three disjoint subsets: the interior of the curve, the exterior of the curve, and the curve itself. I have a triangle drawn on a plane, and we have three distinct subsets: the inside of the curve or the boundary of the curve, and of course we have the outside of the curve. If we have two line segments that intersect, we call that a vertex, and the side of the curve is any segment of the curve. So let's do an example with a simple closed curve. This is a simple closed curve. Although it looks complicated, there are no overlaps, and it does start and stop at the same point. Now the question is x inside or outside of the curve? Well, if you look at it very carefully, if I start at x, I can actually go outside of the curve without crossing the curve itself. So x is outside of the curve. It is not inside the curve. We can actually go outside the curve without crossing the actual curve. There are different types of polygons, and remember, polygons are simple closed curves with line segments as sides. A triangle has three sides. Quadrilaterals have four sides. Pentagons have five sides. Hexagons have six sides. Heptagons have seven sides. Octagons have eight sides. Nonagons have nine sides, and decagons have 10 sides. If we have more sides than that, we typically refer to it as an n-gon. An interior angle is an angle formed by two sides of a polygon with a common vertex. Exterior angle of a convex polygon is an angle formed by a side of a polygon and the extension of a continuous side of the polygon. A diagonal is a line segment connecting non-consecutive vertices of a polygon. Interior angle is an angle that occurs inside the polygon where two segments meet at a vertex. An exterior angle is different, that we have to extend a line segment to the outside of the figure first, then we'll take the angle that occurs between the side of that polygon and the extension of that line segment. Congruent parts are parts with the same size and same shape. Two lines are congruent using this symbol here if tracing of one line segment can be fitted exactly on top of the other line segment. So they're exactly the same copy. I can lay them on top of each other. Two angles are congruent if they have the same measure. Segment A and B has exactly the same distance as segment CD, so they're congruent. Angle XYZ is exactly the same as angle RQP, so they are also congruent angles. Regular polygons are special in that the sides are congruent and all angles are congruent. A regular polygon is equilateral and equiangular. Again, a regular polygon is equilateral and equiangular. So we'll go over some properties of triangles. There are three types of triangles. A right triangle is a triangle that consists of one right angle. An acute triangle is a triangle in which all of the angles are acute or less than 90 degrees. An obtuse triangle is a triangle that contains one angle that's greater than 90 degrees but less than 180 degrees. We can also classify triangles based on their side lengths. A scalene triangle is a triangle that has no congruent sides. All of the sides are different from each other. An isosceles triangle is a triangle with at least two congruent sides, so these two have the same length. An equilateral triangle is a triangle with all three sides being exactly the same length. A trapezoid is a quadrilateral with at least one pair of parallel sides. So these two are parallel with each other. A kite is a quadrilateral with two adjacent sides congruent to the other side and also congruent. A kite is a quadrilateral with two adjacent congruent and the other two sides also congruent. So the two adjacent sides here have the same length as these two adjacent sides also. An isosceles trapezoid is where the base angles are congruent and the side segments are also congruent. A parallelogram is a quadrilateral which each pair of opposite sides are parallel. Both of these are parallel and both of these are parallel. A rectangle is a parallelogram, so all of the opposite sides are also parallel, and the corner is a right angle. A rhombus is a parallelogram with two adjacent sides that are congruent. If you look at the figure, since we have a parallelogram with two adjacent sides congruent, all of the sides are also congruent for a rhombus. A square is a rectangle with two adjacent sides congruent. Since two adjacent sides are congruent, that means a square has all of its sides being congruent and all of the corners are also 90 degrees. So the difference between a rhombus and a square is the angle. The angle for a square is all 90 degrees, while a rhombus has two obtuse angles and two acute angles. Hierarchy among polygons. Polygons can break up into two categories. Remember, polygons are simple, closed curves that consist of line segments. Triangles are polygons with three sides, and quadrilaterals are polygons with four sides. Triangles can be broken into scalene, where all of the sides are different lengths, or at least two sides are the same length, or all of the sides being the same length. Hierarchy among polygons. Polygons are simple closed curves that consist of line segments. A triangle has three sides and it can be broken down into several categories. Scalene triangles are triangles where all of the sides have different lengths. Isosceles triangles are where two sides are congruent. Equilateral triangles are where all three sides are congruent. Quadrilaterals are polygons with four sides. They can be broken down into two categories. Kite, which is a quadrilateral where the adjacent sides are congruent, and trapezoids where opposite sides are parallel. Parallelograms are where both pairs of opposite sides are parallel. Isosceles trapezoids are where base angles are congruent. A rectangle is a parallelogram that has angles that are 90 degrees. A rhombus is a kite that has congruent sides. And a square is essentially a rectangle where all of the sides are the same. Line symmetries. Mathematically, a geometric figure has a line symmetry L if it has its own image under a reflection. In A, we can see that if we reflect this image across this line, it would give us the same image on the other side. There's a mirror reflection on the other side. In A, we have 1, 2, 3 different lines of symmetry, where each line represents a mirror reflection on the other side. In figure B, we only have one line symmetry. There's only one line that would reflect the exact same image on the other side. In C, the star figure here has many line symmetries in which the image is exactly the same on the other side of the line. This frontal image of a boat has only one line symmetry straight down the middle. How many lines of symmetry does each drawing have? The first figure is a hexagon. It has 6 sides. I have a line of symmetry running straight down the middle. Another line of symmetry diagonally. Another one going the opposite diagonal direction. And it also looks like we have a line of symmetry through the vertex and out the other vertex. Similarly here as well. And we have one more line of symmetry. So that is a total of 1, 2, 3, 4, 5, 6. We have 6 lines of symmetry. In B, I could draw only one line of symmetry right down the middle of this letter A. So we only have one line of symmetry. In figure C, it looks like I can draw one up and down and another one horizontally. It looks like we have 2 lines of symmetry. In figure D, we cannot draw a line that has a mirror image on the other side. Figure D does not have a line of symmetry. A figure has a rotational symmetry or turn symmetry when the trace figure can be rotated less than 360 degrees about some point, the turn center, so that it matches the original figure. If you look at the first figure, I could rotate this triangle around the point O less than 360 degrees or 120 degrees, and I would get the same image on top of that figure. Looking at this figure here, which consists of 3 leaves, if I rotate it 120 degrees, I would get exactly the same image. So this also has a rotational symmetry to it around this turn point O. Determine the amount of turn for the rotational symmetries of each figure. In figure A, notice that it splits into 5 symmetrical pieces. I know for a full rotation we have 360 degrees. So I can divide that by 5, and this gives me 72 degrees. So one rotation of 72 degrees will have as a turn symmetry that will yield the same image. But we can do this multiple times. I can add 72 degrees to itself once to get 144 degrees, twice to get 216 degrees, and 4 times to get 288 degrees. Now remember, rotational symmetries has to be less than 360 degrees, so we cannot add 72 more degrees to 288 because it will give us 360 degrees. For figure B, notice that we have 6 pieces that are symmetrical with each other. So we're going to take 360 degrees, divide that by 6, and this yields 60 degrees. If I add 60 degrees to itself once, I get 120 degrees. Do it again, I get 180 degrees. Add another 60 degrees, we get 240 degrees. Add 60 degrees again, we have 300 degrees. So we can rotate this 60 degrees and get the same image, 120 degrees, get the same image, and so on. For figure C, there appears to be only one way I can rotate this, and that's 180 degrees around to get exactly the same image. So we only have 1 degree of rotation, 180 degrees. Any figure that has rotational symmetry of 180 degrees is said to have point symmetry about the turn center. These are some figures that have point symmetry. If you were to rotate each of these figures 180 degrees, you would have exactly the same image for each one of these figures.